Now then, if we're in a situation where we have some sort of significant relationship between two data sets that we've seen using that correlation coefficient and maybe even a hypothesis test on top of it just to be sure, we can talk about actually effectively modeling the relationship between them in order to make more predictions about what might happen for things outside of the data set using a thing called a regression line, or as I said, sometimes it's called a line of best fit or a trend line, but the idea is that you take your scatter plot and you draw into it a line which treats, thinking of this in terms of a function, the independent x values as your inputs and the dependent y values as being something like the outputs, but we don't call that y equals mx plus b like we normally would because it's not exactly always our y values. We instead use the notation y hat for that, and I'll say that sometimes here we have y hat equals mx plus b or b plus mx. Thanks to the commutative property of addition, we can rearrange those. And then sometimes also we'll use a different notation, or instead of calling it m, we might call it a, and then maybe we'll call that one b and the other one a. They get flopped around a little bit depending on the context, depending on the circumstances, but the main thing to understand is we're working from a linear construction, y equals something times a slope plus a constant, where that slope, that's the representative of our rate of change, the rate of change in that relationship that we label here with the letter m, has this formula here, which again looks nasty. I'm not going to read it out, but hopefully this top piece of nastiness is in particular familiar because that's actually the exact same as the numerator, the top of the formula for R, the sample linear correlation coefficient. And that's a meaningful connection because the value m in this regression line is meant to have a very similar purpose to R. It's meant to represent something like the amount of correlation, where, in particular, if m is 0, thinking in terms of a trend line, that would mean a horizontal trend line. If you have a horizontal trend line, as your input changes, your output doesn't, which means you have no relationship at all, so you would expect that R is also 0. And for a very basic mathematical fact that you guys may not remember, the only way you can have that a fraction is 0 is if the top is 0. So if the top is 0 for m, that means the exact same top is 0 for R, and they are both 0 for fundamentally the same reason that we are trying to represent something with a line we really shouldn't, that there is no linear relationship between our data sets. And for slightly more complex reasons, we also have that when m is positive, R must also be positive. That's stuff to do with squares and those radicals that we had in that other term. And when R is negative, so must m be negative. So like I talked about back in 9.1, when we have negative correlation, R is negative, so is m. When we have positive correlation, m is positive, so is R. These things should go together, at least to an extent. Obviously the values for m you're going to see are a little bit different than we might get for R. They can be bigger than 1 and smaller than -1, but the type of connection they model comes from a similar place and ends up at a similar place. And on the other hand, you have this value here that we call b. For those of you thinking back to algebra, is a thing called the y-intercept, but that's the value where x is 0, where we essentially don't have any of our input independent variable, and it's easier to understand what that represents with a specific example, but we'll see that as we're going. When we want to get that value m, what we look at is the average of our y values, y bar, going way back to the beginning with that notation, minus m times the average of our x values. So sum of y over n minus m times sum of x over n, which I think is a little bit easier to read than it is to say just because of, well, how subtle the difference between m and n can be when we're referring to things. But the point is, you take that scatter plot pattern, draw a line in there, and you try to get some sense of what's going on. Where in particular, when we're talking about these things, there's a value that we have to keep in mind. There's a value that we have to work around called the residual. And I mentioned the residual a little bit implicitly in that last video, where I talked about the gap from the line to a specific value. That is, it's the gap between a value we expect and a value that we actually see in our data set. It's how far off our projection is from, in a sense, reality, which doesn't always need to be a single value, because you can have two different things with the same input value. This doesn't need to have that nice function behavior, because we're not trying to hit every single point. But when we're setting it up in this way, we like that value to be as small as possible. We like our data set to fit as close to the line as possible, but we understand that getting something perfectly linear, well, it doesn't happen often, and if it did, then this wouldn't be of any value anyway, because we wouldn't need to worry that much about the prediction. We know it by the pattern really nicely to begin with. So when we're working with these, we like the residuals, we like those differences, we like those jumps to be as small as possible, but they are just about always present, and in a slightly different way, we'll talk about those some more in section 9.3. But for now, what we're going to do is think a little bit more about what this type of thing looks like with an example.